Here we are. Hello, everyone. I'm Maura Pintor, an assistant professor from the University of Cagliari in Italy. And welcome to the Machine Learning Security Seminar Series, where we invite people from all over the world to talk about machine learning security. Before we start, I would like to tell you a few things about the seminars. First, the seminars are live streamed and recorded. So if you want to check out all the past events and even the recording from this one, you will find them in YouTube, in our channel, where you can also find a free course on machine learning security held by our university in the past. And you can find all the recordings there. All right, and I would like to thank all the people who helped me organize this seminar series. And now, after this short introduction, I will give the stage to Giorgio, who will introduce the speaker for today.
Thank you, Maura, and welcome again to everybody. So today our speaker is Adam Dziedzic. Adam is a Tenure Track Faculty Member at CISPA Helmholtz Center for Information Security, co-leading the SprintML group. His research is focused on secure and trustworthy machine learning as a service, and he designs robust and reliable machine learning methods for training and inference of machine learning models while preserving data privacy and model confidentiality. Adam was a postdoc at the Vector Institute and the University of Toronto, and a member of the CleverHans Lab advised by Prof. Nicolas Papernot. He earned his PhD at the University of Chicago, where he was advised by Prof. Sanjay Krishnan and worked on input and model compression for adaptive and robust neural networks. He obtained his bachelor's and master's degrees from the Warsaw University of Technology in Poland. He was also studying at the Technical University of Denmark and carried out in the meanwhile research at EPFL and also worked at CERN, Barclays Investment Bank in London, Microsoft Research, as well as Google. So Adam, we are very happy to have you here as our speaker, and the stage is all yours.
Okay, thank you very much, Maura and Giorgio, for this great introduction. So hello, everyone. My name is Adam Dziedzic, and today I have the pleasure to present to you our work on private prompt learning for large language models. So this work was presented at the NeurIPS conference last year. And if you have any questions during the talk, please don't hesitate to ask. And you can do it either just by unmuting yourself and just speaking loud, or just sending maybe a message on the chat, and we can check it out and then answer the questions. So without further ado, let's begin. So nowadays, large language models, in short LLMs, underpin a broad range of services. So thanks to them, we can obtain high-quality translations of a given text. For example, here from English to Italian. So probably now I should say buongiorno. And then LLMs perform a plethora of language tasks. So OpenAI exposes its GPT-3 model via ChatGPT. Probably nowadays it's ChatGPT-4 that underpins ChatGPT. And these models perform various text generation tasks. So for example, you can use ChatGPT to recite the first law of robotics or generate a poem, or for example, you can paste a dialogue and ask for summarization. So it's really fun to play with these models. They generate useful content like beautiful of these birthday wishes, but also sometimes it's also scary how good these models are. And then the only disappointing aspect is that sometimes they have hallucinations, so they just make up some rather unrelated stuff. And personally, I still find them really fascinating in the way how can they improve, for example, the quality of our writing. And then what's more is that these models can also, for example, generate code. So OpenAI's codex system translates natural language to code. You can type a comment in the text box on the left-hand side, and then seek the corresponding code on the right-hand side. And then Clarify went even a step further. So this company has a platform where other companies can deploy their models, especially LLMs. And this is done in the pay per query setting, where users query their models and pay for the answers. So this platform exposes models for vision, NLP, and many other domains. And you can, for example, use models such as Roberta to find useful embeddings for example, a piece of text. However, here behind the scenes, to create such large language models that underpin these ML APIs, it is really a costly venture. And there are at least three main factors that contribute to these high costs. The first one is that it is hard to collect and clean large amount of data, especially here these models are trained on the scrapes from the internet. So they just crawl the internet, they just copy all the text possible that they can really gather and then just train on this text. Second, we also need to hire ML experts to tune Habe parameters for these models. And then usually it's really quite costly venture to do that. And these models are humongous. There's also a lot of expertise going into parallelization, how to really run this training of these models. And then finally, we also need expensive hardware, such as GPUs, TPUs, or many CPUs, for both actually, for training as well as the inference. And it was estimated that, for example, a single training run of GPT-3 model costs north of $12 million. So unfortunately, most of us cannot probably afford training such LLMs from scratch. So the main question here is really how we can adjust these LLMs to our own needs. And then there are nowadays many different ways how to do it. And then we call this, in general, these methods how to tune these models for our own needs. We call them general adaptations. So here I will present three main ways how to adapt LLMs to our specific downstream tasks. So currently, the most popular way to adapt these LLMs is through prompting. So this is noted as this one in the figure. And soft prompts in the first category of these adaptations, they are a learnable set of parameters that are prepended to the input embeddings. Then prefix is similar to soft prompt, but apart from being prepended to the input, it can also be prepended to every attention layer in the LLM. And then the input prompts can be also discrete, where you prepend additional natural language text to your standard input. This is probably the most known version of prompts. They'll also touch base more on these different kinds of prompts and tell you more about soft prompts and prefix in the next slides. For now, let's focus on these adaptations. The second type of adaptations is just we call that inner fine-tuning. So here you can either fine-tune the whole model, meaning that you adjust all the parameters of the LLM, or you can use some other methods, for example, low-rank adaptations such as LoRa, where you just adjust the small parameters that are added within the layers of LLMs. And there are also so-called output last layer fine-tuning methods, where you just usually adapt a couple of last layers or even add additional layer on top of these existing LLM. So what are the main differences between these different methods, especially between prompts versus fine-tuning? So prompt tuning only requires us to store a small task-specific prompt per each task. And this enables multitask inference using the original pre-trained model. So we need to store only a small prompt per task with around 10K parameters. And most importantly for this soft prompt or prefix is that in a single batch, we can include prompts from many different tasks and even from many different users. So this makes usage of LLMs much more efficient. On the other hand, if we just use fine-tuning, then this requires us to store a separate copy of the model per task. So this, of course, is a cost in terms of storage, but also compute, because we cannot really do any like batch processing for different tasks from different users. Here, for every single task, we have to have LLM with like billions of parameters. And currently, for example, like what is estimated is that GPT-4 has more than 1 trillion parameters. So this is a humongous number of parameters, and storing such models separately per each task is, of course, rather prohibitively expensive. So then what really is the way to go is that we have to just try to find out what are the methods by prompting to adapt these LLMs. And then because of that, we'll focus in the rest of the talk on these prompts, and we will discuss both discrete prompts that are just prepended text to the inputs, as well as we will talk about soft prompts and prefix that prepend additional parameters before your input. So let's focus first on this latter, the soft prompts and prefix. So soft prompts are simply learnable set of parameters that are prepended to the input embeddings. So here you are given the example of a patient who has a heart pain, and the task of the prompt is to classify the patient as healthy or not healthy, so sick. So the words from the user's input are first tokenized, and each token receives is expressed as an embedding. And here we embed the token, first token being heart, and the next token being pain. And this is prepended with the special token for classification tasks, just the CLS token. And then once we have these embeddings, we are in the embedding space. And then here we also add additional parameters, which are exactly these soft prompts before these embeddings for the classification token. And then the number of token embeddings that we can add for the soft prompts usually is between 1 to even 100. And we usually observe that if the task is more difficult, we need more parameters, so then we actually have bigger soft prompts. Apparently, from increasing number of embeddings that we add through the soft prompt, we can also attach additional parameters within the attention layer. So there can be additional input to the attention layers within the LLM. And then with that change, we call it prefix, which is a soft prompt attached to basically every single layer of LLM. And again, with prefix, we even can have more parameters than with soft prompt. And then potentially we can, for example, cater to more difficult tasks. So now we want to train this soft prompt or prefix. And then here the task is to give a sentiment of a patient's state. So we want to, again, state if the patient is sick or healthy. So for a patient's input text, in this case being this input heart pain, we append the CLS token and also the soft prompt. And then the text is transformed to the input tokens and then embeddings after the forward pass. And here we do forward pass to the whole LLM. We compute the class label with a linear model at the end of the LLM and perform standard optimization. But here, instead of modifying LLM parameters, we update the soft prompt parameters. And then here it's important actually that the backprop to change the parameters of the soft prompts has to be done through the whole model. So potentially it is also discrete prompt at the inputs. You just can take some data and just do standard training on this data, where you only change the inputs to the model. And also, usually I can give you example, like for these soft prompts, the embedding can be, let's say, the single token, something like 768 parameters. And the soft prompt consists of one or more of such token embeddings. The length of this soft prompt is also limited in the terms of the context size. If this is not enough, this context size for the soft prompt, then we can expand and use the prefix to further increase number of parameters that we want to tune for a given task. Okay. As you can see, because we have to do backprop to the model, then usually these soft prompts are possible to adjust for the open LLMs. So open LLMs means that these LLMs release their source code. So for example, models like Llama, Vicuna, you can access their source code. So then you can indeed run something like this soft prompt tuning or prefix tuning on these models, because you do have access to the parameters of these LLMs. Some APIs, as far as I know, one of them from NVIDIA also can also supports soft prompts, but this is something that is not very common. So this potentially can limit the use of the method to primarily open LLMs. And then the question is, okay, how can we adapt LLMs in other ways? So maybe I could just ask us if there are any questions from the audience regarding maybe.
Maybe I have a quick question.
Okay,
Can these techniques also be combined in the sense that I can apply an input tuning and then also some fine tuning together?
Yeah, very good. Actually, indeed, this is a very good idea. And we even had initial tests. We actually had tests of these things already. And indeed, it can increase the performance. So we do have something like, for example, combining soft prompt or prefix with LoRa. And then through the fact that we adjust more parameters and also we adjust different parts of the model really, then indeed it can give better performance than single method on its own. So we observe indeed synergy if you can combine some of these methods.
All right.
Very
And
good.
the other question I had was when you fine tune one of these models, is it mostly supervised or also unsupervised, or
yeah, very good
depends
question.
on the task probably?
Yeah, it depends on the task. So here actually I present tasks like classification, which is fully supervised, and also tasks like for example, dialog summarization. So this is also supervised because you get proper loss. You basically, for a given dialogue, you expect a given summary, and you just compute loss through how the output from the model, for example, summary that model outputs agrees with the expected summary. So this is like a standard supervised learning. Here, I think that it is. I can imagine that it is also would be potentially useful to do something like self-supervised learning for LLMs. So you can just fine-tune a given model to specific, let's say, domain. So let's say that you have a general purpose LLM, and then you want to fine-tune that to, let's say, only medical domain. So potentially you can just train the model or fine-tune the model just on the patient's, let's say, records, and then through that you might just tune the model using self-supervised learning.
Okay, thanks.
Yeah, very good question. So any other questions from the audience? Okay, so if not, we can probably move on. So apart from this soft prompts and prefix that you just tune parameters in the input embedding space, you also can just attach additional textual context to the model. So of course, if you use APIs such as one from OpenAI through GPT-3 or GPT-4, let's say Turbo, or use something like Claude from Anthropic, then usually they provide you a possibility of prompting the model, meaning that you attach context in the sense of discrete prompts. So discrete prompts usually consists of two parts, namely an instruction telling the model what to do with the input, and also these prompts have a private demonstrations, which also are called shots. So I will refer to them usually as shots. So these shots provide an example or examples of how to solve a task at hand. So if we want another LLM to recognize whether the sentiment of a movie review was positive or negative, a discrete prompt could look like the one on the green background. We tell the model to classify the movie review as being positive or negative, and give the model examples of how to do it. So, for example, if the input is this film is a masterpiece, then the sentiment of this movie review should be positive. And then what is really nice about this discrete prompts is that there is no backprop required. So this is a bit cheaper in terms of that you don't have to do backprop to the whole model, but you do have to tune these instructions. You have to also select these examples, these shots for the prompt. So there is also a lot of engineering required from just individuals who want to have such prompts, and also many of the trials and errors to really find out which kind of instructions or which kind of demonstrations, shots really work well for a given LLM. So then once we have this prompt here, also known as prompt template, we prepend this prompt to a given input. So here a new input is something like the movie was great, and we would like model to classify what is the sentiment of this movie review. And then we pass this, so we basically prepend this green prompt to this black new input, and then the model in this case should return the answer positive. Okay, so now the question is it really enough? So in terms of especially privacy, and once we started our research on these topics, little was known about the privacy implications of prompts. And what we first did was that we instantiated the membership inference attack against a prompted GPT-3 model. So our membership inference attack asks the simple question, given a data point and the prompted LLM with the prompt, we ask, was the data point used as an example in the LLM prompt? So was this given, let's say, sentence or patient's record used as a shot in the prompt? And then to answer this question, we rely on standard techniques from prior MIA attacks, so this membership inference attacks. And we compare the model confidence on the true output label between member data points and non-members. So by members here I mean that the data points that were used as shots in the prompt. And also we compared these confidence scores for non-members. So these are data points which were not used in the given prompt. And intuition is simple that if a model has seen a given example in the prompt, then the confidence of the model for predicting the correct label would be much higher than when asked with an unseen example. So here, since we operate with generative models, we take the tokens that the class labels belong to, for example, positive or negative, which are output by the model, and which are the labels for the inputs. And we observe that there is significant privacy risk for the data points used as examples in prompts. And then adversary might even go a step further, so and attempt to directly extract the private demonstrations of these shots. So even not just inferring if a given shot was in the prompt or not, but directly trying to like output this shot from the prompt. So this is called also a jailbreak, where one tries to fool the model, where instead of like fulfilling the given task, the goal is to extract the private data from the prompt. So if the private demonstrations are data from clinical, for example, reports, then this is really a severe privacy violation. And then regarding these attacks that we carried out, for example, for membership inference attack for prompts, we carried this attack using GPT-3 model. We prompted this model with examples from the Wikipedia dataset that classifies the topics of Wikipedia articles into 6 classes. So the left figure here confirms our hypothesis that the prompted LLM is significantly more confident on the member data points than non-members. So here members are just these blue colors, these blue columns. Non-members are these orange colors. So usually the confidence of these members is significantly higher, close to 1, whereas for non-members, these confidence values are usually very low and close to 0. So through that, we can really simply distinguish between data points that actually were used in the prompt versus those which weren't. And then we also have this standard way how to show this performance of a prompt. So here on the right-hand side, we have a UC log curve of our membership inference attack. And this shows how well the model can tell apart these members and non-members for this metric. So the further apart the blue line is from the diagonal red dashed line, the more effective the membership inference attack is. Looking at the result, we see that clearly there is significant privacy risk for data points that are used as examples in prompts. So here the average AUC score was roughly 0.84, which is very high. So this really confirmed that we do have this potential risk of private data leaking from prompts. So this is the main outcome of this analysis. And then our main question was how to really provide prompt learning for large language models that can actually preserve the privacy of the private data used to tune or adapt these large language models. So are there any questions regarding maybe this part, regarding how we attack the models? What is the threat model?
Actually, I wanted to know, because the distribution looks, the distribution for the non-members, there is a spike also at 1. Is it because there is a softmax in the end, so it squeezes all the values in 1, or is there a reason for that?
Yeah.
So there is a spike at the end. Yeah.
Yeah. Also, what is really interesting is that from previous research, what actually we observed is that these large transformers also generalize pretty well. So some examples might not be in the, for example, prompt or in the training set even, but these LLMs can generalize very well to these examples. So usually we observe something like they do generalize very well and they also perform quite well and are confident about a given example, or they just fail and this is like confidence close to 0. So I think that this is kind of this dichotomy in these results.
I see. Yeah, the other question was probably related to that. What happens if you take one of the sentences and change a few words? For the members, of course.
Yeah, so we also just this kind of like this contamination a bit. So it of course depends like how big is your perturbation, how far you are from the original sentence. So for example, just if you replace maybe just a few words with like synonyms, these models also perform very well on these examples. However, if you of course perturb this input sentences too much, then at some point you just lose the signal and you don't detect this example as being really a member. So this really depends on the perturbation size that you incur in a given example. Also, there are trials of membership inference attacks for the even data that were used to train the LLMs, and then usually they do something like this. So there's a couple of actually papers about MLaaS for LLMs, but for the training data themselves. And then indeed they use something like intuition that even if you perturb a given sentence with, let's say, synonyms, or you even remove some words, or you maybe add some words, then still the model, if model saw such example during the training, and the model's confidence or basically predictions on this or perplexity, for example, on these examples is higher than high performance of the model on these examples than on non-members. So this is a standard also way how to do really MLaaS for these models.
I see. Okay. Thank you.
Yeah, very welcome.
Are there other questions from the audience, or I think they would have raised the hand by now? Okay, yeah, you can go ahead.
Okay, sounds good. Right. So yeah, so our question was how we can provide private prompt learning for large language models. So before we delve deeply into how to prevent the privacy leakage from prompts, I have to give you kind of a crash course introduction to the concepts of differential privacy. So in short, differential privacy is a mathematical framework to implement formal privacy guarantees. So intuitively, the outputs should be roughly the same, or so-called indistinguishable, independently of whether or not a given data point was used to learn a prompt or not. So here we consider prompts, and then this roughly same outputs of a pair of prompts which were created through datasets D and D prime. So these are the neighboring prompts, and they differ only by a single data point, by a single shot within the prompts. And then the main inequality for DP, and then we have this main parameter epsilon. So this determines how close these outputs of the model should be, despite the model being trained on dataset D and D prime. And then parameter, and also we have ds, which is a set of possible outputs, and the parameter delta is the probability of a failure. So the similar concept to cryptography, where there is a small probability that, for example, adversary might guess our private key. And the upper M here is a randomized mechanism. So in general, for a DP, we have to provide some form of randomization to protect privacy of the private data. Okay, so after this very, very short intro, we can move on to the standard algorithm to train machine learning models, which is just SGD. So to start from the very beginning, we have as input, and then the input is soft-prompt with parameters theta. So these are these input embeddings that we want to adjust for a given task. And we have some loss function upper R. We also provide this learning rate eta, and we consider upper T training rounds. So we start from selecting a data point x sub I, compute a gradient for this data point, and finally we take the gradient, take the opposite step to the gradient. This is how we standard way train ML models. And then to obtain this canonical algorithm to train models with privacy, which is called DPHD, we have to add only these two red lines. So we add two additional privacy parameters. So theta determines how much noise for privacy we add, and the norm bound C is the norm for clipping of the gradients. So we do not want a gradient from a single example to have too much influence on the trained model, so we clip that. So basically we clip the gradients for each data point. It's also kind of similar to gradient clipping to tackle the problem of gradient explosion. And after we clip the gradient, we also add noise to the sum of the clipped gradients. And this is to protect further privacy, because the random noise added also prevents us to guessing who were the individuals trained a given model. So this is standard DPHD. And then we leveraged this framework, and we basically incorporated this into DPHD algorithm that we used for soft-prompts. So here we start from initial parameters for the soft-prompt embedding. So this is this free rectangles for the soft-prompt parameters, and we prepend these parameters to the embeddings for a given input. So this input can be, for example, this patient's state, let's say heart pain. This can be input, which we embed. We also actually have labels for these data points. So as Maura was asking, this is this classification task, so the standard supervised learning. And then once we have that, we pass this whole soft-prompt embedding prepended to the input. So we pass to the LEM. We have this label, so we can compute the loss function. Once we compute the loss value for this given examples, we can just compute the gradient for the soft prompt. And then once we have the gradient for the soft prompt, we just do standard clipping of the gradients. So for each data point separately, we sum these gradients and we just add noise to protect privacy. So then through that, we obtain these privatized gradients, and then we use them to finally update the soft prompt. So this is the standard method how we do this computation of the privatized gradients and updating them with the soft prompt. And then we observed that for standard NLP datasets like SST2, where we have to find out what is the movie sentiment, the review of the sentiment of a given review, the performance of the soft prompt is even higher than for a full tuning of the model, and then even works better in this case than prefix tuning. So in general, for the soft prompt here, we have a very small number of parameters, only 10,000, whereas, for example, full fine-tuning of the model would require us to tune all the, in this case, 125 million parameters of the models. So with the soft prompt, we can obtain, in this case, much higher performance at also good privacy level, %8, and of course, much better than full fine-tuning. We also tested on other standard classification tasks for NLP, such as QNLI. So this is the test from Stanford, which is about question answering. And then the task is that we have to determine whether the context sentence contains the answer to the question. So this task is slightly more difficult than SST2. And then the performance of the soft prompt matches the performance of full fine-tuning. But in this case, we can also use prefix to just have more parameters for more difficult task. And in this case, prefix tuning can outperform soft prompt or full fine-tuning. We also ran the prefix tuning for the text generation tasks. So this is some standard test actually this done for LLMs. So here the task is Samsung. So this is dialogue summarization task. So for a given dialogue between two people, we have to just summarize what was in the dialogue. And to assess how good the performance for this task is, we use this Rouge scores. So for Rouge 1, for example, we look at unigrams, whereas for Rouge 2, we calculate the similarity of all 2 grams. So we just see how many of these unigrams in the output from the LLM agrees with the unigrams that were given as the gold standard. So what should be predicted. And then Rouge L is just the similarity of the longest common subsequence between the output from LLM and the expected output. So what we actually observe is that the prefix tuning using our method with PromDPHD performs on par with other methods and also uses much fewer parameters, for example, than full fine-tuning. So this is really good also because prefix tuning, apart from the fact that it uses fewer parameters than full fine-tuning, it also has the advantage of exposing multitask batches, meaning that for a given model that for which we have a prefix, we can just run through the model during inference in a single batch many tasks, as well as do this task for many users. So then it is, of course, much less costly than LoRa or full fine-tuning that required us to have separate model per each task. So is there any question regarding PromDPHD?
I have a quick question, which is not strictly related to PromDPHD, but just a curiosity.
Mm-hmm.
So far you talked about soft prompts, right?
Right.
But I'm wondering why not discrete prompts? So I'm wondering if actually this is applicable also to discrete prompts, for instance.
Yeah, very good. So we will talk now about discrete prompts.
Okay.
So this is great, I think, segue to the next topic. In short, to answer your question, Giorgio, PromDPHD is just for this soft prompt. So when you adapt parameters, and of course, we have to use different techniques for discrete prompts. So this is because discrete prompts cannot be tuned by gradient descent. We cannot use DPHD for them. So discrete prompts are useful if we want to leverage these closed LLMs, such as GPT-3 or GPT-4 from OpenAI, or for example, Claude from Anthropic, where we have only access to the a model through prompting, and we can only just attach this additional prompt before other inputs. So for this kind of prompts, for the discrete prompts, we actually use, we leverage another framework from privacy for ML, which is called PATEI. So PATEI stands for Private Aggregation of Teacher Ensembles. And then to implement PATEI for discrete prompts, here I describe basically the whole schema, how we leverage PATEI for these discrete prompts. So we start with our private labeled data, and we divide this data into many subsets. We call them partitions. So these are non-overlapping subsets of the data set. And then through these different subsets, we create prompts. So basically, each prompt contains a disjoint set of examples or shots from this private labeled data. So this is an example of this many different teacher prompts. We call them teacher prompts. So this is not in PATEI. So in PATEI, you would have to just have many different models, each trained on the subset of the training data. But here, for the LLMs, we have many different prompts, and each of them just contains some examples from the training set. And then the data from this private training set just serves as demonstrations or these shots. Then, once we have this teacher prompts, we use unlabeled public data to query the LLM with the private teacher prompts. So here you basically have in blue this unlabeled public data, and then we just pass them through LLM. So how do we do that? Is that we take this given example and we just append to the given prompt. First, 1 second, and so on and so forth until the last prompt. So each of these prompts serves as teacher, for which each teacher actually wants to label this example. So from all of this teacher, what we can create actually is histogram. So same as in PATEI in this case. So histogram in this case is for movie reviews. So we have two classes, positive. So each teacher contributes 1 vote if the class is positive or negative, and we just collect these votes from all of these teachers into the histogram, and we have the vote counts per each class. So the first, after we have this histogram, we just then on top of these vote counts, we add Gaussian noise. So this is just standard noisy argmax. And then once we have this noise on top of the vote counts, we then take the argmax and then return this maximum value, which serves as label for a given example. So once we have labels for all of these examples, we use this now labeled public data to create a new so-called student prompt. So this is not like a model like in PATEI that we have to train model from scratch, but we have another prompt. So how do we find this prompt? Is that we take all of this now labeled public data and we select which of these examples from the public labeled data are really the best performing for a given task. So we just pick and choose the best examples, and from them we create these shots for the new student prompt. So then once we have this student prompt, it serves for further data points that come to our API to answer some questions. It serves as this final public prompt. Okay, maybe are there any questions regarding this prompt PATEI method? Okay, apparently not. Okay, so let's move on. So once we have this student prompt, we just want to analyze what's the performance of this new prompt. So here we use for this experiment, we use GPT-3 model with the DVpedia dataset here with 14 classes. And then what we here have is that first is a 0 shot. 0 shot means that we don't have any demonstrations, no shots, just instruction. So for example, instruction is something like tell me what is the topic of this article from Wikipedia, but no examples how to do it. So absolute equals 0, it's like perfect privacy. We don't give any additional examples from, let's say, private data set. There might be some leakage of the private data through the instruction, but usually here for these tasks we just have standard instructions, so there is no really leakage for the instructions. And if we just have zero-shot prompts, then performance is relatively low. It's only 44.2%. Then also we compared what's happening if we just have teacher ensemble. So no noise, no privacy. We just use this many teachers to compute the final labels for this unlabeled public data, and then just check what is the performance. The performance is roughly 2 times higher than a zero-shot. So once we give some examples how to solve a given task, then performance increases dramatically. And finally, what we find is, I think, very interesting, is that PromptPay has a very low privacy requirement. So here epsilon is really low, only roughly 2. And then even though this is very strict privacy guarantee, we have a very good performance of 80.3%, which is just slightly less than performance for the teacher ensembles with no privacy. So this was a really good result for us, that PromptPay can really dramatically help to leverage discrete prompts and still preserve privacy of private data. We also ran PromptPay with other and compared with other data set, other methods. So here what we actually are doing is that we again test PromptPay for the Samsung data set, which is dollar summarization, also epsilon equals 8. And here we compare actually different ways how to adapt these LLMs. So DPICL is another method that was proposed actually also last year. And then it leverages GPT-3, DaVinci. In principle, DPICL is just a method similar to Pate in the concept to just answer queries privately. So it has kind of limited number of queries. Actually, it has limited number of queries it can answer for a given user. We also tested here private LoRa on a Vicuna 7B model and our PromptPay with OpenLlama 13B. So what we actually observe is that PromptPay in this setup, even though it's run on the open model, it performs much better than DPICL and on the DaVinci model. And the performance is significantly better for PromptPay. On the other hand, if we have this full access to the LLM, and we can have resources, we can afford to fine-tune the LLM, for example, using private LoRa, then we can even get a better performance if we just use Vicuna 7B. And to just give you estimation, so for example, GPT-3 DaVinci has roughly 175 billion parameters. So this is significantly more than, for example, Vicuna 7B or OpenLlama 13B. So we observed that here we can get a really good performance if we just do this fine-tuning of the models on these local open models. Okay, so this is a very, I think, interesting result. And then to summarize, we learned that we can perform an efficient adaptation of LLMs with prompts. And we can use either soft prompts, prefix, or discrete prompts. Then we observed that the prompts might actually leak private information about our sensitive data. So we showed how to do it, for example, using the membership inference attack. Finally, we also showed 2 methods how to learn prompts with privacy. The first one is PromptDPHD that enables us to train soft prompts and prefix with privacy by clipping the gradients and adding noise to the gradients. And finally, we also showed PromptPay, which allows us to protect our private data for discrete prompts. And this method leverages an ensemble of private teacher prompts and uses the noisy argmax mechanism, like in the Pate framework, to release the labels for unlabeled public data in a private manner. So with that, thank you for your attention, and I'm happy to answer any more questions.
Thank you very much, Adam. So are there any questions from the audience? Just raise your hand or, open the camera if you have. In the meanwhile, maybe I can ask one, or Giorgio, Giorgio, do you?
No, you can go ahead. I'll ask after you.
Okay. Yeah, I wanted to know, because you're using a pre-trained model, right? So you have guarantees, of course, on the learned task, but does this change anything on the previous model? So what if my training data was already in the model, used for the model?
Yeah, so I think that this is a problem of contamination. And then it apparently, based on the latest results, I think that the final, answer is not there yet, to just really verify clearly if a given model was trained or not on a given data set. I think it's a quite difficult task. We have some, I think, ideas how to solve that. And it's really a problem because if you, for example, a provider of a closed LLM would like to really get higher performance on some specific tasks, they might really include these tasks into the training of the whole LLM. So this is, I think, one of the problematic things, but also to really for example, do this analysis, I think fairly, because ultimately, for example, what I showed, let's say, let me just see. Yeah, so here we compare actually relative difference between these methods. So let's say for each method, we use the same model. So here we use for each method PyTHIA 1B, so 1 billion parameters for the PyTHIA model. This is from this famous PyTHIA suite of models. And then it's the same task. So direct summarization. We also have the same parameter epsilon equals 8. So we just really want to have very controlled experiment. So in PyTHIA, for example, 1B, we know this is open source model. We know exactly what data was used to train the model. So let's say in this example, we have full guarantee that Samsung, this summarization task dataset, was not in this LLM.
Okay. Yeah, I was thinking of maybe doing a membership inference on my data set, just to check if the model replies very confidently. And then if I discover that some of the samples are actually already learned by the model, can I do something?
Yeah, this is a very good question. So this is something that is called unlearning, and there's also active area of research. And then there are, I think, currently, research endeavors to try to unlearn a given example from LLM. I think it's in general a very difficult problem to do it, but I can imagine that there are some ways how we can, at least to some extent, mitigate the fact that maybe your data point indeed was used to train a given LLM.
I see. And did you see any active research on that going
Yes.
on? Is it?
Yeah, so actually, I saw effort about that to tackle the problem. Yeah, for example, I think that there were some ideas to do it kind of iteratively. So, for example, let's say if you have a very few samples to unlearn, you can just always prompt your LLM, so prepend some examples and always say that never output anything like these examples or do something about these specific examples. If you have too many points to unlearn, maybe you can fine-tune the model to, for example, make sure that loss value on these examples is just lower. It's not perfect, but I think that in some sense there are this kind of attempts to mitigate the problem.
I see. Okay, I'll leave the space for other questions.
Maybe I can ask if nobody's. Okay, so I'm just curious about whether, what's the state, let's say, in defending against privacy attacks in LLMs? I mean, how are defenses typically built, if whether they just use like differential privacy, and in general, how these how defending against these attacks in LLM is scaling with respect to how bigger these models are getting and how much data we are using.
Mm-hmm. So I think that what is interesting is that these models in general are trained on a large amount of public data. So the models themselves can contain different examples from the internet. So I think that usually we don't want to protect all the data that is in the world. We just want to protect specific private data that, let's say, individuals, companies have. And then once we have this like big model pre-trained on large public examples, then we fine-tune this model or adapt to specific downstream tasks. And they are usually much smaller than the public data that was used to pre-train the LLM. So then, for example, here we have this, I primarily talk about two types of prompting. So soft prompt or this prefix tuning and discrete prompts. So they are relatively small, right? This is, for example, like for a discrete prompt, you just attach some demonstrations. So this is relatively, I think, small. And even I think I gave some examples that for, let's say, like this simple task, we have like less than 10K parameters to fine tune for the given task. And then full model in this case is 120 million parameters. So this is kind of good, I think, area for DP, differential privacy. We can just leverage the PhD, for example, to tune this prefix or soft prompt. And then I think that, it was our actual idea, really, that we can really do that. And also it performs pretty well for different tasks. And then for discrete prompts, it's the same. I think that because ultimately users' data are much smaller than the public data, then the methods to adapt the models are also relatively efficient to run, and also to protect them is also, I think, potentially feasible to do, right, for us. That's also why we just target primarily these methods, how to adapt LLMs. We don't say that anything that we would like to do DP for the whole model, starting from scratch, training whole model on private large amount of data. We just focus on this something like tasks that really are, I think, the main focus on individuals' private data. So this is actually, I think, a bit smaller scale than just full training.
It's manageable. Thank you.
Okay, there's space for another question.
We have a question.
I see something in the
There's
chat.
some question from Luca.
Okay, just just
okay.
unmute yourself. Yes.
Okay, can you hear me?
Yes, we can hear you,
Yes.
Luca.
Okay, thank you for your talk. So at the beginning of the talk, you mentioned also the fine-tuning, and so my question is it possible to do an attack, something similar to the attack that you presented? Like, can you extract some information used during the fine-tuning, or maybe there is also another way to specialize the LLM using the RAG? Is it possible to do something similar also against these two methods? And if it is possible, is it also possible to use the differential privacy to mitigate this risk?
You mean something like membership inference for full fine-tuning?
Yes, for the fine-tuning, or also for the RAG.
Oh yeah, okay. Indeed. So there are actually, so what actually here present actually is also prefix tuning with the PhD, full fine-tuning with the PhD. So there are methods from ICLR 2022 that present basically how to do private full fine-tuning of the model, as well as prefix tuning with also privacy. So indeed, there are methods that do that. And they are also kind of like now, I think, become quite established, I think, in this area. And also they work very well. And then what is important is that regarding the first part of the question, if we can run something like membership inference attack against the fine-tuned models, indeed, like LLMs also can be fully fine-tuned, right? And then what's happening actually is that in general, I think across all the models that are like this so-called foundation models or like large models, it's much easier to run a membership inference tag on a fine-tuned model to just detect if a given data point was used to fine-tune the model than to run MIA on the whole LLM. So indeed, like there is for sure a problem with this fine-tuning that we can do MIA much easier than for whole LLM, but at the same time we can also do the PhD fine-tuning or the PhD LoRa to have these models adapted with private data.
Okay, thank you.
Welcome.
Thank you, Adam. I think, okay, I'll close the streaming now. Then if there are other questions, maybe we postpone them, or you can reach out to him. So thank you again, Adam, for the talk and for answering these many questions.
Yeah, my pleasure. Thank you very much.
And thanks to everyone for joining today. See you next time.
See you.
Bye-bye.
Bye.
Thank you. Bye-bye.
Bye.